this session, we will see how to make use of the ARM processor, ARM-7 processor, which is made by Philips company LPC2148. The reason for choosing LPC2148 is if you compare the family of LPC series, LPC2148 has 32 kilobytes of static RAM plus 8 kilobytes of additional RAM for DMA controller, that is for USB. Then there is 512 kilobytes of on-chip flash. There is a inbuilt DTA converter of 14 channel, A to D converter of 14 channel of 10-bit resolution, and there is a inbuilt DTA converter of 10-bit DAC, and two serial ports are there. Second serial port UART is with full FODEM interface. So this is a 64-pin microcontroller which is having ARM core as a architecture. If you see the internal features of the LPC21 series, mainly LPC2148, one is about the crystal. The crystal which we connect for this LPC2148 is 12 megahertz crystal here, which is internally uses phase lock loop to multiply this crystal frequency by 5 times so that the controller can work up to 60 megahertz. The ARM core is ARM-7 TDMI-S series, which has JTAG interface. Then internal memory, which is the flash 512 kilobytes, static RAM of 32 kilobytes maximum, and then various peripherals like general purpose IOs, that is port 0 and port 1. Port 0, as you can see, from 0 to 31 bit, and port 1 from 16 to 31. Input output lines are there, and these port pins are also having multi-functions, that is peripheral functions like PWM0 to PWM6. Then there is a DAC output, ADC input channels, 14 channels are available here. Then there are timers, input capture feature, then external interrupts, watchdog timer, real-time clock RTC, two serial ports. Second serial port is with full modem signals. Then serial peripheral interface, I2C bus, USB bus. So these many peripherals are integrated in LPC2148 along with the ARM-7 core processor, and of course with the high-speed internal buses for interfacing the memory, that is your RAM, and as well as the interfacing the peripherals, which is a peripheral bus, VPB bus. About the pin configuration, LPC2148 is a 64-pin IC, as the most important pins for any controller is the VDD, ground VSS, then the crystal interface XTL1 and XTL2, that is pin number 61 and then 62, which is what we call as a minimum system design. So once you connect the VCC, that is VDD, ground, then the crystal, then almost interface is done. Once that is done, one can interface the reset pin, so that reset is active low. So whenever active low is signal is given to reset pin, the microcontroller will enter into the reset state. Then other interfaces like as is there, like IO ports, then the external interfaces like serial ports, then timers. So all those pins, almost every pin is having multiple functions. So by through software, the functionality of the pin has to be selected. The D plus and D minus is for USB interface. So ARM core, that is LPC2148, has a inbuilt DAC USB interface. The board, that is ARM-7 LPC2148 board, as having the following features. This is the LPC2148 64-pin IC. This controller receives the power by using this USB interface. So this USB also meant for communication. At the same time, it also provides the power supply. Programming of this LPC2148 is done with the help of the serial port. So computer serial port is connected to this 9-pin D-type female connector to program it. While programming, there is a jumper here, what is written as a in-system programming. So this jumper has to be closed and press the reset button. So once you press the reset button, the LPC2148 will enter into the bootloader mode so that it will accept the external program. Once the programming is done, then remove the jumper, press the reset button so that application program will be executed. The controller operates on 12 MHz crystal, which internally multiplies by 5 to work on 60 MHz. In order to interface the serial port to the microcontroller, there is a DC to DC converter driver is connected. So with the help of these 4 capacitor, it will convert 0 to 3.3 volt signals into RS232 through standard signals. Since USB gives the power, that is 5 volts and 500 milliamperes, there is a regulator IC is there, 1117, which will convert 5 volts DC into 3.3 volts form. Then the other interfaces are, there is a LCD interface, which is a 16-pin connector. A text LCD can be interfaced to this LCD, to this microcontroller, and there is a SD card, SD flash memory can be interfaced in this slot. Other I/O lines are available on this slot, and there is a opto isolator is available, which can be connected to the relay. The DAC output is available here, and A to D converter inputs are available here. So you can give analog signals on these pins. If you look at the circuit diagram, the LPC2148 is a 64-pin IC, which is a LPC2148, which is a TQFP package. As shown in the figure, the minimum system design for this is where as the power first of all is drawn from the USB connector, and this USB power supply is connected to 1117 IC, which will be convert this 5 volts into 3.3 volts form. Or external power supply also can be used with the help of the 7805 regulator. The external power has to be in DC form, where this DC is again converted to 3.3 volts. So either you can use USB as a power supply or external DC, where you can connect a 9 volts DC adapter here, so that the 7805 regulator will give 5 volts, and in turn this 5 volts is regulated by this 1117 LM1117, which will give 3.3 volts. So microcontroller operates on 3.3 volts power supply. So since the mode of operation of the microcontroller is decided by this ISP, so whenever this jumper is closed, that means whenever ISP is connected to ground, then the LPC is in ISP mode. Whenever you remove the jumper, then this pin is connected to VCC by 10 kilo ohms resistor, which operates on application program mode. Reset is signal is connected here. Since it is an active low signal, whenever you press the reset button, the reset signal is connected to ground. The microcontroller operates on 12 megahertz external crystal, which is connected on pin number 61 and 62. There is another source of clock, which is a low frequency clock, 32.768 kilohertz, which is meant for a real time clock. The programming of the microcontroller is done with the help of this TXT and RXT signals, which are there on P0.0 and 0.1. Since this is operating on 3.3 volts, so it has to be converted into RS-232 standard. So MAX 3243 is a DC to DC converter IC where TXT0, that is this, RXT0 is connected to this driver. So in turn, this IC will convert the output signal, that is pin number 3 of the serial port and pin number 2 of the serial port in RS-232 form. That is, voltage levels at pin number 2 and 3 are plus 12 and minus 12 volts, where this COM1 port can be connected to the computer for programming. So 4 capacitors are used to build the charge of plus 12 and minus 12 volts. So even this IC also works on 3.3 volts power supply. There is an additional serial port is available on COM2, which can be used for interfacing either ZigBee or Bluetooth devices. The board also has a provision for interfacing a text LCD. As shown, 16 pin connector is available, where the ports DB0 to DB7, that is port 1.16 to 1.23, is used for interfacing the LCD data bus, that is D0, that is pin number 7 to pin number 14. The handshake signals of the LCD, that is RS, read oblique write bar, and enable, these three signals are connected on the microcontroller. RS is connected on port 0.2, read oblique write bar is connected on port 0.3, enable is connected on port 0.4. So the LCD is using 8 lines for data bus and 3 lines for the control signals. There is a provision to interface the graphics LCD, which is a 20 pin connector, and most of the signals are same except the CS1, CS2 signals. There is a provision to interface the SD card flash memory to the ARM processor. So the SD card programmed by using serial peripheral interface, that is MISO, MOSI, SCK, and select lines of the microcontroller. That is, these are the signals which are meant for SDRAM interface purpose. The D2A converter output, that is port 0.25, is available on this 2 pin connector. A to D converter IO lines are connected on this 5 pin connector, that is port channel number 0.1, 0.2, 0.3 is available on this connector. There is only one LED interface, that is port 0.31, which is connected to the LED, which is a common anode. So whenever you make this pin as a 0, then LED will be on. So this is as far as the external interface is concerned. There are few pins are there for like interrupt 0, interrupt 1 of the IO lines of the ARM processor, where can be used for interfacing any external sensor boards. Similarly, ADC is separately brought it out here so that it can be connected to some sensors like temperature sensor, pressure sensor, humidity sensor. The DAC output is also connected to a amplifier, which is audio amplifier, so that the output of the DAC after amplification, it is available on the jack, so that either headphones or a low wattage speaker can be connected at the output stage for playing any songs or music. So this board is useful even for implementing the file allocation table, operating system, and then creating a files in the SD card, and then selecting the file, writing the data to the port so that even the MP3 player songs also can be played through this DAC. There is a provision for interfacing optocoupler. This PC817 can drive the relays. So the microcontroller IO line, that is port 1.24, is meant for the relay driver, optically isolated. So there is a JTAG interface provision is there. JTAG pins are brought it on P1 connector, 5x2 connector, so that in case of a external JTAG debugger interface, one can make use of this port. The board side, as can be seen, SD card is placed here, LPC21xx is IC, and then MAX3243 is this. Programming is done by serial port. Power supply, that is either through USB or a adapter, can be connected here. There is a reset switch, and then there is a ISP pin, in system programming pin is available. There is a text LCD which has to be mounted inside the PCB, can be connected here, and DAC output is available here, relay is available here. When we choose the compiler for writing the programs for this board, there is a choice of choosing the compilers. Either one can choose KEIL as a compiler, or one can choose GNU, that is open source, either in Linux, or even KEIL also supports GNU toolset, or ARM ADS, or IAR workbench. So how to choose a compiler? There are some parameters which are mentioned on the left side, and on the right side the values are given for a given test bench. So for a identical conditions, how a KEIL Microvision simulator performs for various compilers is given here. So there are two test benches are there. One is dry stone, other is the wet stone. So that means when you are working on dry stone, you are not using any floating point arithmetic operations. This entire program, this entire testing platform is done using integer numbers. However, when you are using whetstone, it is very specific custom design where there is one can use the floating point arithmetic operations. So this kind of conditions, if they are done, then one can compare what is the execution speed for given application. One can notice that execution speed should be always high speed, that means in microseconds. It should take less time to execute it. Then when you are using those integer numbers in case of this platform, then how much time it is taking to execute those numbers. Then similarly, the uh, total code size, that is your program code size, once you compile, the footprint should be as small as possible, so that it is a optimized code. So that is the flash memory or program memory space. Similarly, for that given program, how much amount of stack is used, that means how much RAM space is occupied, it should be as less as possible. Then the data size depends on that given application test bench. It should occupy as less RAM as possible, that is a buffer space. So similarly for the second test bench, the parameters are same. Only thing is this time it is floating point arithmetic operations may be performed. So again, how much time it is taking for execution, how many instructions are performed, right? So in this case, as you can see, 5263 instructions are performed, which as is a pretty high as compared to other controllers. Then optimized code is generated, stack size is less, and similarly amount of data occupies is 72 bytes. So this is how one can choose the compiler for a given platform. So we will be, just to begin with, we will be using KEIL as a compiler for writing the programs for this ARM process. Now let us see how to use the KEIL environment for programming and simulation. So we are using KEIL Microvision UV4. We will practice first how to use the KEIL compiler. Then we will see around 20-25 examples in this environment how to simulate it. First, you can go to the project, then manage. You can see there is a components, environment, and books. You can set the help where one can choose the folder extensions for the help. Before that, you have to create your own group so that for that group this help will be available. So I will open one project, existing project, where blinky dot uv file, add group, let us write a first example code in assembly language of ARM processor LPC2148. We will use KEIL compiler, which is a evaluation version. Up to 32 kilobytes of code you can write. KEIL Microvision 4, which supports ARM processor, various variants of ARM processor. The first step to create a to write a program, first we'll have to create a project. So project, and we'll have to say new Microvision project. Then wherever you want to create the project, for example, in my documents I want to create a project. So new, create a folder, say YSR. Now in this folder, what is the name of the project you want to create? Say for example, add is the name of the project I want to create. So the next step is for which target device you are writing the program. Because though you are talking about ARM processor, but there are number of companies who manufacture the ARM processor. For example, we are using Philips NXP. There also you can see various models. The difference is whenever you select a ARM processor, you will notice the features of the ARM processor. So just we will discuss more about the details. So we are using LPC2148 in this example. Now this is asking, do you want to add the startup file. We say no, because later on I will tell you what do you mean by startup file. Now our project is created. Now you can create a new, you can write a new program. So write a assembly language program, how small it may be, then type your own assembly language. I have one small program, for example. Let me show you a small program where a assembly program is written. As you can see, a very small program. Okay, so whenever you create a project, when you write a project, you have to save it. So now it is asking in your project file, project folder, what is the name of the file. So I will say add dot s, because we are creating assembly language, not C, remember. Save. Okay, now see, the even the colors are changed for immediate values, hash, and then the color is pink. That is how it recognizes this is assembly language. You have written an assembly language program. So first line should be always the reset interrupt vector. So this is by default are the directives of any assembly language program you have to write, and saying this is a code. Then entry means that is a starting instruction of the program. I repeat again, there are no files which are added here, only a simple assembly language program with the extension of .s. And the program is very simple. We have loaded decimal number 25 in one register, decimal number 204 in other register, and after addition we are storing the result in R2. And that's all. We have terminated the program by using a directive called end. So entry is the starting of the instruction, end is the end of the instruction of the directive of the program. That is how the assembler recognizes the starting and ending. By default, you must always start your program with the reset interrupt vector. So, but then we have only written the program, save it, but we have not added this program as a part of our project file. So go to your project, right click, and you say add your extend your project file. So source group, in source group, right click, add files to groups. Now you can add as many files you want. We have written a assembly language program, that is S is the extension, add, close. Okay, now you will, if you, when you have extend this your group file, you will find that add.s is now added in your project group. Now your compiler recognizes that for a YSR folder, add is your project name and add.s is your name of the file. Okay, there are few things you will have to configure. Go to project, then options. So do not make any changes, say okay, again go to project, then options for target. Second time when you choose, first device, verify whether the correct device is selected or not. Now it is LPC2148. Target, what is the operating speed? Yes, 12 megahertz is the operating speed. Then do you want to use the internal ROM and RAM? Yes, so these two things should be selected. Output, yes, create hexa file, so that when it compiles we want hexa file, that is the absolute file which need to be loaded on the board, and give the path so that where it automatically it recognizes the path where your folder is created. Then the last thing you will have to do is go to debug. So by default we want to use the simulator, we do not want to use any board right now. Says okay. So now compile your program. As you can see on the output window, there are no errors. Your program is compiled and it has created a hexa file called add. So that completes that. The program doesn't have any syntax error. Now syntax error means, say for example, if I don't give any comma, then if I compile it, then you will notice the errors, syntax errors are displayed. It is not recognizing the name of the resistors. So that is what you will have to, by using the assembler, first you will have to remove the syntax errors. Now how to find out the logical errors in the program. Logical errors means there is a possibility that instead of using one resistor you are using other resistor, instead of one number you are using other number, and so on. So for that there is a debug option. Go to debug, say OK. Now you will see when you select the debug option, various windows are open. Left side is your ARM processor CPU registers. Top is your as equivalent machine language hexa addresses of after assembling, and this is the source file which you have written. Now this yellow cursor indicates that now the program counter is currently positioned here. Now you can see on the left side, all along with the all CPU registers, it also has the your program status register as well as the various modes of operations and their corresponding um, like say registers which are applicable to that mode, and then program counter and the mode states. Okay, now you will have to do the single stepping breakpoints and so on, which we will later on use most of the features. So just to begin with, as you can see, there is a step function is there. So if you do the single stepping, as you know, this 25, which is a decimal number, which is equivalent values 19, is loaded in R3 register. In the second step, you will see 204 is loaded in R7 register, that is CC. In third step, you will find that the R2 is updated with that, but then the problem is it has, after that it has there is no instruction is written here. Now there is a interrupt is generated. That interrupt is called, that exception is called prefetch abort, because it's not recognizing after that there is no instruction. So that is why now it has entered into the supervisory mode. Okay, now if you can stop it, now you see R2 is the last value is E5, which is the after addition whatever is the current result. So this is how one can write assembly language program and simulate it. Now let us see some more programs. You can go to project, open project. So in your Mtron ARM kit folder, you will find there is a folder called KEIL ASM. So first you have seen some of the numbers. Let us see some other example. In this example, if you want to remove any file, you can remove it, and if you want to add any file, you can very well add the examples, whatever the examples you want. So first open project. It's already open. In this example, what you can notice is that program is same, except that there is one more instruction is added, BAL to stop, so that at least the program is continuously is executing the BAL instruction, which is an infinite loop. So if you compile this program and if you simulate the program, and when you single step the program, you will notice that no exception is generated and no abort is generated. So the program is continuously executing the BAL instruction. So this is how one can avoid the exceptions by terminating the program. So there are number of example programs are there. You can say, for example, instead of this file, you can remove this file, and then to this group you can add some more examples, which is a assembly language, say log.s. So this example, in this example, as you can see, few more assembly language programs are written. You can compile you can simulate them by using the KEIL compiler. So as you can refer the data sheet from the Gibson textbook, you will find number of assembly language programs, more than some 40-50 example programs are written, which you can test all the instruction set of the ARM processor as well as some of the applications using assembly language program like BCD conversion, ADC, GPIO, block transfer, etc. So this is just to begin with how one can write a assembly language program and compile, simulate, generate a hexa file by using KEIL compiler. Now let us see how to write a embedded C programs, and we will see some more functions of the KEIL compiler which are useful for testing and debugging various peripherals of the ARM processors. Now let us see how to use KEIL as a compiler for writing the programs. When you open a KEIL compiler, first go to project, then new Microvision project. You can give some, you can create your own folder, say new folder. Give project name, save. So the second step is it will ask for which ARM processor you want to write the program. Though you are writing for ARM processor, but there are so many companies who manufactures the ARM processor. So in our case, we are using NXP. In NXP again, so many ARM processors are there, LPC21xx. As you can see in the description, though we are using ARM-7 as a core, but the features are different from company to company and IC to IC. The difference in terms of memory, the difference in terms of peripherals, the difference in terms of pins. If you say OK, then it is asking, do you want to add a startup file? If you say yes, then you will see there is a startup file is created. We will discuss about this startup file at a later stage. Now you can go to project and let us set the environment. In manage, components, environment and books, go to folder extension options. There use real view compiler should be selected, so that whatever is the folders, extensions, books we are going to refer will be referring this real view compiler. Then go to books. In books, for example, we want to refer the data sheets. So which data sheets we want to say, for example, LPC21xx is the PDF file which we want to have a online help. So select the correct PDF file which you want to have a online help. Or else when you select the data sheet, you can change the book, whichever is the PDF file you want to view from the directory C KEIL ARM processor is the path. So this is for the online help. So once the environment is selected, now we want to create our own C file. So say for example, you can go to your project, left click and right click, and then you can add any files which if they are already written. Say for example, there is a program called main.c. So if I left click on this, as you can see, a C program is written which will switch on or switch off bit number 31. Okay, so go to project, then here we already selected the device, but we need to select the other compiler options. So options for the main file. So once you select it, as you can see, the C++ environment, by default, whatever is the options are selected in for the compiler is as is. We enable ARM or thumb internetworking. We have enabled thumb mode, right? And so these options are by default create executable linkable functions. So these are the options we want to use, the default options. Then again go to project, then options, now this time for the target device. So target is first device we have already selected LPC21xx. In target on our board we are using 12 megahertz crystal. So make this as a 12 megahertz crystal. That means 12 megahertz as a clock frequency. And the code generation we want not thumb mode. Thumb mode means it will generate the code for 16-bit, but we want ARM mode, that is 32-bit. So keep that default as it is. Do not use the off-chip memory because on our board we have not interfaced any external memory, but you must select this on-chip ROM as well as RAM. Both the things has to be enabled. So once you verify whether internal ROM, internal RAM is selected or not, then let us look at the output. By default, create hexa file is not selected. So you have to select create hexa file, and then where you want to save that file, you select in which folder you want to create the output file along with the file name. Then let us not change the default values of the other options. Go to the linker. In linker, you select this use memory layout from target dialog. So that has to be selected from the target layout. And then go to debugger. In debugger, we want to use the simulator, not the debugger. So if you select this, then you require a KEIL company's debugger for programming the kit. But since we are not using that, we are using a third-party solution. So we use a simulator environment. And while loading the program, we are selecting load application program at the startup, and we are saying run to main. So while simulation, we want both. One is a startup file, and then that has to be run up to main. See, both the simulation environment we have set. So these are the two options. You have to select it, and then you say OK. Okay. So once the debugger environment is set, then compile the program. Then at the output file, it should show 0 errors and the hexa file is created along with the size of the code and amount of memory it has occupied. This completes the compilation of the program where there is no syntax errors. So syntax errors means, say for example, if I don't give semicolon, if I compile the program, now it shows that line number 24 there is a error. So if you double click on this, then it will directly go to that line where error is there. So unless you remove the syntax error, target won't be created. Okay, let us compile the program. By any chance, if you have a KEIL company's debugger, then you can see the option that's called download the program. That means now it will directly load onto the target board. But however, we are using a simulation environment, so let us select the debug environment. So since we are using evaluation version, your size of the code can go up to 32 kilobytes. Okay, so in the debugger environment, as you can see, the left side, the ARM processor, the register set, 32-bit registers are available, and then it also has the modes of operation, as you can see right now, fast interrupt mode, interrupt mode, supervisory mode, abort mode, undefined mode. Depending on your which mode of operation, the set of registers are shown, how they are affected, along with the contents of the program counter and the CPU internal cycles. So in order to simulate the program, you can see the debug options. One is single stepping, then step over, step in, then run to cursor, breakpoints. One can set the breakpoints. So to execute the program, right now as we have selected in the simulation environment, run to main program. So that means now your cursor is set at the main program. It won't execute your startup file. Okay, now if I do single stepping, as you can see, the instructions will be executed. But depends on your requirement, which peripherals you want to view, which registers you want to view, then you will have to enable peripherals. For example, if you want to view the contents of the ports, then you select the port bits and you make them visible on your workspace. Similarly, if you want to view any memory content, serial windows or logic analyzers, so those windows can be enabled so that while executing the program, you can view the contents of the ARM processor. If you want to execute the whole program in one shot, then press F5, that is run. Then as you can see in the program, bit number 31 is set and clear. So this bit will toggle of the port 0. So this bit will be set or clear, depending on the amount of delay you have introduced in the program. So this is how one can verify the logical mistakes in the programs. If you want to see the assembly code of the program which you have written, then there is a DAssembly window. You can open at any point of time this view DAssembly window, which will show the equivalent code for the C program. As you can see, left side the address of the, see this upper portion is the code which you have written. The left side is the address of the program memory space and its hexa values and the corresponding the machine language. Like as you can see in the program, whatever the program instructions which you have written, the equivalent assembly language program is written, is done by this part is done by the compiler. Okay, so if you remember, there is a wait loop is there. So equivalent code for the wait loop is assembled at member location 264 onwards. Then there is a while loop, IO set, dir instruction. The equivalent code for this is this. Your main program, as you can see, your main function is starting from 220 location. So once you compile the program, the compiler will create first assembly language, then its equivalent machine language. Okay. So if you want to know how this code is going to be stored in the flash memory, there is a watch memory is there. You can see memory window. So if you are interested in looking for the location, let us say 220 location. As you can see, whatever is the code stored in the 220 location, that will be reflected here, right? Say for example, you have some variables, right? So the variables they are there in 290. Some variables are stored, so defined double word. So 290, if you see, right? So those variables are stored in these locations. So if you want to see 0 x 0 0 0 0 290, you can see in this location the value which you have stored is MSB is 40, LSB is 60. So 40060. That means this 40060 is stored in memory location 290. So that is this. So this is how, even while executing the program, if you are interested in watching the variables and their status, then in the memory window you can type the hexa value physical address, then contents are shown here, and the red color indicates those are the variables which are modified. Okay, similarly, looking at the program, you can go to the symbol uh, window, where in your program how many symbols are there. Main is there, where I is the variable, wait is there, here there you have a count, there is a I, there is a j. So these are the various symbols which are used in the program. Now as you can see, for the main and the wait, right, main is assembled at 224 and wait loop is at 1F0 is the address, physical address of the symbols which are used in the program. So these locations you can actually compare in the main program. For example, 224, right? So you can see the 224 is nothing but where your main loop is starting from. Similarly, 1F0. So 1F0 is your the delay program, that is your wait program, which you have written in this location, right? So this is how the symbols and their corresponding addresses are represented here. And in watch window, if you are interested in monitoring any variables, say for example, as you can see, I have entered value j. So now as the program is getting executed, then whatever is the values are reflected here. Or similarly, if I want to add one more variable here, let us say I want to add I. Okay, now as you can see, the contents of I is shown here. So like that, you can watch the variables, you can watch the memory locations, and you can see what are the physical addresses for the corresponding variables. And you can also see the equivalent assembly language code for the C programs in the D-assembly window. This is how one can use the KEIL debugger to debug the program, to monitor the variables which are getting modified while executing the program in the ARM processor. Okay, so after completing the first exercise, now let us do the second exercise. Second exercise is to understand what do you mean by startup code. In KEIL environment, whenever we create a project, the compiler asks for an option, do you want to add the startup code or not? So if you add a startup code, what exactly happens? What do you mean by this configuration file in a startup file? Okay. This, since the ARM processors we have seen, ARM processors are manufactured by several companies. Every company has a series of ARM controllers. Now it is user's choice which ARM processor you select. So when you select a ARM processor, say for example, go to project and open project. So this time we are working example number 2 startup code. So startup.uv project. So if you open this, right, so as you can see, there is a startup code is also is a part of your project. So in this project, when we are talking about the uh, target device LPC21xx, so remember the startup file is created for that particular LPC series. So when I said LPC21xx, that means even the startup file is meant for that microcontroller only. So as you choose a different controller, it will be a different startup file. So startup file is not same for controller to controller. Okay. So what is this startup file? What are the contents of this startup file? As you can see, whenever a startup file is there, there is a configuration wizard is there. If you look at the configuration wizard, then it shows what are the things you can configure. Say for example, stack configuration. So stack configuration means what is the address you want to assign to a specific uh, mode of operation. Let us say whenever there is a undefined mode is there, so then you want to reserve this space, these many locations. Or if you want to get a supervisory mode, then how much stack you want. Abort mode, how much stack you want. Then fast interrupt mode, how much stack. Interrupt mode, how much. Then user or system mode, what is the stack size. So similarly for heap configuration, then PLL setup, and memory accelerator. So these are the things either by using GUI you can configure. Whatever changes you make here, the same thing will be reflected in your system file, that is a startup file. Okay, so whatever, like say for example, just now we have seen how to set the contents of the stack size. Now as you can see, your undefined is 00, then the supervisory mode is 08 location, abort is 00, like that the same contents will be reflected here. So startup file is majorly allocating the space for the interrupt vector table, allocating the space for the stack, initialization of the ARM core peripherals. So there is a difference, that is peripherals which are there in LPC2148 is different. The peripherals which comes as a part of the ARM core is different. Like for example, you know timers, you know IO ports, A to D converter, DAC. These are the external peripherals. But the peripherals which are part of the ARM core is like PLL or the memory accelerator or the clock dividers. So these are all the peripherals which need to be configured irrespective of the application. So if this is not done, if the startup file is not part of your main program, then your application program won't work, because you have not initialized the interrupt vector table, you have not initialized the operating speed of your microcontroller, you have not initialized the stack of your program. So then what happens is, these are all assumptions, so it may lead to conflict. But since as you can see, this is a huge code, we do not want to write on our own. We will let us use the option provided by the compiler itself. And then as you can see, the startup file is always in assembly language program. But then if you remember, while simulating, when we selected the debug environment, that time when we said project options for the startup file, right there, if you see the options in simulation in debug environment, we said run up to main and load application at startup. So that means we wish that the startup file should be part of our simulation environment, and then by default, whenever we simulate, the startup file should be automatically executed, so that while debugging, it will start the debugging from our main function. That means the our debugging should start from here, simulation should start from here. Otherwise unnecessarily you will be doing the single stepping in the startup file itself. So that is the purpose of start from the main function in the debug option. Okay, so what is there in the startup file? In the startup file, as you can see, whatever is the modes of operation is there, then those modes of operations, the flags bits are defined here. Then whatever is the size of the stack you want to define for the various modes of operation is defined here. Then the as you can see, the clock divider for CPU, since the microcontroller, that is ARM processor, is working on 12 megahertz clock, but then we are using the PLL phase lock loop, and the peripheral bus derives the clock from the PLL. So operating speed of the ARM processor, operating speed of the peripherals is depends on the configuration bits of the PLL. So PLL phase lock loop for the microcontroller configuration bits are defined here. So this is by default the PLL multiplication factor. As you can see, we have selected 5, so that whenever the microcontroller starts, it multiplies the external crystal, which is 12 megahertz, by 5, so that it works on 60 megahertz. And similarly, there is a memory accelerator, so that since the microcontroller is inbuilt the flash memory as well as the static RAM, so the bus speed, the data transfer is taken care by the memory accelerator controller. And then about the external memory controller. In our case, we have not interfaced any external memory controller. Otherwise, there is signals are defined for interfacing the external memory. Okay. Then about the interrupt vector table. As we know, every controller has a reserved space for the interrupt vectors, so that whenever a specific interrupt vector is received, it will go to that specific location, and that ISR routine will be executed. As you can see in the vector locations for all the interrupts, reset vector, undefined instruction, software instruction, then abort, program abort, data abort, and some reserve space for debugging. So these interrupt vectors are loaded. As you can see, the instruction says LDR program counter with that address. Those labels are defined here. Whatever their equivalent ISR addresses will be loaded into the program counter, so that whenever a interrupt is received, then program counter will be loaded with that ISR address. Okay. So the interrupt so this is how the initialization is taken care. We have seen how the variables are defined in the above program. Now the external memory controller, the peripheral divisor, and the PLL is configured by using those control words by using the assembly language program. And then about the interrupt vectors. So whenever for example, undefined instruction is received, then the first thing is it will change the mode of operation into the undefined mode. Then it will initialize the stack pointer, and then it will calculate the stack size. So these are the three instructions which are there in every ISR, so that it will take care of the switching of the task, initialization of the stack, and calculating the size of the stack for all the modes of operation. So that is the meaning of um, initialization of the ISR routines. Okay. So once this is done, once the stack is initialized, once the ISRs, interrupt vector tables, are initialized, once the peripherals are initialized, then as you can see, the program comes here and load the R0 register with the main code, C code. That means your main function, wherever the starting address of this main function, that will be loaded into the register, and then as you can see, branch to R0. That means now, since the complete startup code is executed, now it will enter into your main program, and then it will start executing from here. So that is why the initialization of the hardware, that is the ARM core, we do not want to write every time. So whenever we create a project, we always include the startup code, so that the hardware initialization is taken care by the startup file. Then we will only concentrate on our application program. For as per the application program, if you require any timers or interrupts or IO ports, then user has to write his or her own initialization code in the main program. So that is the significance of the startup file. I request all of you to create a project, add a startup file, and go through the contents of the startup file and simulate it. So this completes the second example in KEIL environment, how to create a project, how to set the debug environment, how to do the single stepping, and how to execute in various modes of operation, how to watch the variables, and then finally, whenever you create a project, what is the significance of the startup file. Okay. With this, we will start now the application programs. Okay. So next example, example number 3, is to demonstrate how to switch from ARM mode to thumb mode. Go to project, open project. Then as you can see example 3 in solutions, thumb code, open this y.uv, open. This project is already open here. So what you can see about this program is that this program consists of some functions. This is the main program, but somewhere we said that call the thumb function. Now as you can see the syntax, the that is pragma thumb, right? That means we are telling the compiler that the following code has to be converted into thumb code, not the ARM code. That means when I say pragma ARM, that means this following code is a 32-bit code, but when I say pragma thumb, that means this following code has to be a 16-bit code. That is how the interleaving happens, switching from 32-bit code to 16-bit code. Now let us see how to set the environment. When you go to the project and when you say target options for the target in C++, make sure that you have enabled the arm oblique thumb interworking and you have unselected the thumb mode, so that it will switch the enable the switching between arm mode to thumb mode and vice versa. Okay, so this option has to be selected. And now compile the program. No errors. Now let us debug the program. So in the debug environment, as you can see left side you have the ARM processor, and then this code where the equivalent code of assembly language is there on the top portion of the window. Now I will do the single stepping by the F11, as either you can press hotkey of F11 or you can press this button. So when I execute this instruction, as you can see left side the contents of the registers are modified. But this time I want to monitor CPSR register, that is a status register. In status register, as you know, there is a thumb bit. Right now, since it is in the ARM mode, this bit is 0. The moment when I execute the thumb function, you will notice that this flag will be set to 1. And similarly, since this at present the pragma ARM mode is there, that is where the equivalent code for this is, as you can see here in assembly language window, which is a 32-bit code. But you will notice that when I enter into the thumb mode, then the code will be 16-bit. Okay, let us do the single stepping. Now as you can see, I am at the thumb function. If at present thumb flag is 0, but if I do single stepping, now you can see thumb mode bit is set, and similar in the CPSR register, and similarly the program has entered this pragma thumb, which is a thumb function. Now in DAssembly window also, if you notice, the code size is 16-bit, not 32-bit. So that is the interleaving, internetworking between the ARM mode and thumb mode. And if you now the entire code, whatever it is executing, is all 16-bit code, right? So unless this delay is completed, it is always in the thumb mode. So once again, if you come back from this loop, again it will go back to the ARM mode. So that is how one can mix the, or one can switch the ARM processor from ARM mode to thumb mode and vice versa, so that as and when required 32-bit operation, one can work on ARM mode, and as and when 16-bit code is required, you can work in the thumb mode. So with this, it completes the simulation of the internetworking of ARM mode and the thumb mode. Okay, now let us see the next example, exercise number 4, which is in KEIL compiler, KEIL environment. What are the standard input output functions? What are the libraries which are meant for standard input output functions? In most of the microcontrollers, the standard input output libraries are meant for UART, that is serial port. So in KEIL also, your printf and scanf statements are meant for serial communication. That means whenever you say printf, that means the microcontroller will transmit the data, whatever you have mentioned in the codes, through serially. And whenever you say scanf or get character statement, then it will receive the data through serial port. So that is how the most of the embedded compilers works. The standard input output libraries are nothing but serial communication. So let us write a program in KEIL environment. You can go to project. In open project, you can see the fourth example, standard input output. You can open this hello.uv project. There first you can look at the hello.c code. First as you can see, the standard input output library is included, and since we are working on LPC21xx, that header file is mentioned. In the main program, as you can see, the control registers meant for initialization of the peripheral of the ARM processor is done. Like as you can see, the pin selection, that is RxD pin and TXD pin of the ARM processor. Remember, we are using ARM processor has two serial ports. One is TXT0 and RxT0, and other is TXT1 and RxT1. So that means port 0.8 and 0.9, they have multiple functions. They are not only as a IO ports, they are also act as a TXT and RxT pin. So since at this point of time we are not interested using them as a IO ports, we want to use them as a serial communication. So we will have to, the in pin select control register of the ARM processor, we'll have to use it RxT and TXT pin, that is 5 is the value which will enable the peripheral port. And then the control register for ARM processor serial port for initialization is in UART protocol. We want 8-bit data, no parity, and one stop bit. So the control word is turns out to be 83. Then in your DLL register, you can load the baud rate value of 9600 as a baud rate value, and then you can make the DLAB value as a 0. Okay, so this will complete the full duplex mode of operation and the baud rate of 9600. As you can see in the while loop, we are saying printf statement. Some string we want to transmit. So, but this printf is nothing but it comes from the standard IO library. Okay, so let us compile the program, right? So zero errors. Now let us simulate the program. In simulation, now since the microcontroller is transmitting the data through serial port, so in watch window, right, in view, you will have to see serial windows second UART, because in this program we are using UART2. So if you enable this UART2, then this window will be open, second UART window will be open. Now in this case, since we are only interested in application, so let us execute the program in one single run. Press F5. So if you execute the program, as you can see, the ARM processor with the specified baud rate is transmitting the string on UART2, right? So that is the meaning, in fact, of the serial port. The ARM processor, in ARM processor KEIL environment, your standard input output libraries are nothing but serial port. Similarly, you can also view the peripherals, since we are interested in UART, not 0, UART1. Now you can view the contents of the UART1 also. What is the effect of these contents? So now the next example is about external interrupt, that is INT0 or INT1. So to use this facility, how to write a program in Microvision 4, let us say example number 5. So as we have seen, whenever we create a project, we also make use of the startup file. In the startup file, the interrupt vector table is initialized and their corresponding addresses are initialized. That is, in this example, let us see how to make use of the fast interrupt through INT1 pin. So in Microvision, as you can see, project, open project. So we are working on interrupt. You can open this project. Okay. So in the main program is about initialization of the fast interrupt request, which is one of the mode of operation of the ARM processor. So before you write the code, you can also configure, go to project, and in options for the project which you have created. So second time if you select, in the linker environment, one must use memory layout from target dialog. So this has to be selected. Then this interrupt structure will work. Okay. So in the main program, first we have called fast interrupt request initialization, which is a function call. So first we are, since whenever a interrupt request is received, we want to indicate that status on LEDs. So we are using port 1, that is bit number 16 to 23 as a output port. Then we want to generate that interrupt by externally generating a signal on external interrupt INT1. So in the pin select control register, uh, instead of IO, we'll have to make use as a external interrupt. Then similarly, we'll have to enable the in vector interrupt controller of the fast interrupt request, and we'll have to clear the peripheral interrupt flag. Say for example, in vector interrupt controller, in the data sheet, if you refer, so first external interrupt, if you want to use the external interrupt, then there is a interrupt register which will enable the INT0, INT1, INT2 external interrupts. So in this register, one has to enable the in our case we are using EINT1. This has to be enabled. Okay. So as the note clearly says that uh, uh, the corresponding bit in EXTINT register must be cleared whenever you are not using, or otherwise you will have to set it. Similarly, the in vector interrupt controller, where we'll have to first of all select we want to select either the slow interrupt request or the fast interrupt request. So in the interrupt select register, we'll have to, out of these 32 interrupt requests, we'll have to enable that fast interrupt request for the EINT 1, and then that particular bit has to be enabled in the enable register. So these two registers has to be enabled. So that is the reason in the program VIC INT select is loaded with 4 zeros and 8 000, so that it will enable the INT1, plus in the interrupt controller it will enable fast interrupt request and clear the flag. Okay, so as mentioned in the description, if this bit is 0 in the select register, the interrupt request with this bit number is assigned to the IRQ0. If this bit is 1, then the interrupt request with this bit number is assigned to FIQ. So since we are interested in making that bit as fast interrupt request, so this bit has to be set in the vector interrupt controller interrupt select register, that is this register. Okay, so once the initialization of the fast interrupt request is done, then initially we have cleared all the bits of the port 1, and wait, that means wait in a infinite loop forever. So then if any interrupt occurs on INT1 pin, either through switch or externally by some signal, then the program will enter into this interrupt service routine, that is FIQ handler, which is the syntax for the fast interrupt request. So in this loop, in this ISR, we have said that the LEDs, alternate LEDs, that is bit number 16 to bit number 23 will be set, and then it will clear the flag of EINT peripheral interrupt flag, and again it comes back and wait in the loop. So let us compile the program and see what is the effect of EINT on fast interrupt request. Now one more thing is, whenever in this example, if you clearly notice in the debug environment, in the project options for the project, in the debug environment, this time we have not selected run to main program. That is because since we are interested in knowing how the fast interrupt request is being generated, so even we want to watch the startup file, what is the effect of the interrupts, interrupt vector locations whenever interrupt request is generated. So we are not selected, we have not skipped the startup file for simulation. Okay, so in this program, we want to see the GPIO 0, then GPIO 1, then we want to see in system control block, we want to see the external interrupt, what is happening on EINT1, so external interrupt. So this is, I mean, the status of the peripherals we want to see. One more thing is, since I mean, in this program we require a external signal to be generated in the EINT pin. So KEIL has a provision to write a script to generate a signal on the pin. Say for example, the script goes like this. If you say signal void toggle on port 0 with XR operation of 4000, so and you can create a button. So if you this button, through this button we can also generate a signal. So that script has to be mentioned in the initialization file. One can write a script for simulation purpose so that some buttons can be created, and that file has to be included in the debug environment and the use simulator, and here that is initialization file. So in I'll go back to the project options for target. Now in debug, as you can see, initialization file. So in initialization file, if I can select the script, whichever is the script you have written, say open. So now the script is as a part of your project. Now if I go to the, if I compile it, and if I go to the debug environment, now if you want to see the button, now view, tool window, now you can see the generate external interrupt 1, which is a script. The script is available here, whatever is the script is written here. Same program, signal void toggle. So that script is available here for this tool, which is a user defined button. Okay, now if you reset the program, now if you execute the program, if you run the program, as you can see now initially IO diagram number 16 to 23 is set, because that's what is the program says, that whenever you call this function, first this IO direction register, these bits will be set. And then after that, if you generate a, by using this pin, if you generate a external interrupt, Say for example, this act as a switch in our case. So if you press this button, now you can see the uh, the IO set, that is the value which is written in the interrupt service routine, that is the 55, that is loaded. So either you can use this button which is defined by the user, or else forcefully you can set or clear this interrupt pin, that is in GPIO 0 bit number 14 is the external interrupt one. So I will reset the program, I will stop executing, reset the program and run. Now this time I will be generating the interrupt. I forcefully set the bit or clear the bit. Now as you can see, the same action has happened where the IO set is loaded with the 55 value. What you can see in the flags is, say for example, right now it is in the user mode, right? The mode is user mode. Now if I select this bit of the interrupt, okay, now as you can see, entered into the fast interrupt request mode. uh, so FIQ bit is set. Similarly, if you see the contents of CPS, can monitor the status of the CPSR whenever I toggle this bit, right? So these highlighted bits are really, you can see the EINT interrupt status also whenever I toggle this bit. And in assembly language code also, it will enter into the interrupt service routine whenever I toggle this bit, right? So by using